Is this showing on the screen? Oh yeah, okay. Okay, I'll just make some apologies for Steve. He had a prior commitment and he wasn't able to make it today, so you're going to have to make do with me, I'm afraid. I just wanted to, first of all, put up some more general slides on the purpose of geochemical characterization, partly just to set the scene for the kind of work that we did for this section of the studies. The purpose really is to, there are three themes. First of all, to evaluate the potential for weathering of mine wastes and for that weathering to affect the chemistry of water that comes into contact with those wastes. The second theme is to inform the engineering design of waste and water management strategies. There are management strategies that can perhaps control, influence or prevent the weathering of the materials, or if the weathering can't be prevented, can perhaps contain or treat any of the weathering products that are formed. Both the outputs from both those themes provide input to the overall assessment of water quality effects, if you consider that some of those weathering products might mix with the wider environment and cause detrimental effects to the local water quality. The whole thing's an iterative process, so clearly depending on a mine plan and the kind of engineering options that are being considered for the site in question, that can affect the potential for the weathering that can take place, and the whole thing's very iterative. The sort of work that was presented in the EBD document in the chapter is very much focused on the first theme, the evaluation of the potential, and Kirk went through some of the kind of basic concepts that we were looking at there. What I would like to demonstrate through the presentation, at least I hope I'm going to demonstrate, is that the type of samples that we've studied and the breadth of data that we've collected can be fairly readily adapted to the second themes at such time as a mine plan does become available. One of the important water chemistry parameters is pH. The solubility of many trace elements is very pH dependent, and the little graph on the left there shows the solubility of aluminium as a function of pH, and you can see that the solubility varies over many orders of magnitude depending on the pH of the water. So geochemical characterization often focuses on the potential for pH changes in the contacting water and trying to understand the resulting effects on trace element concentrations. So there's two very important pH modifying processes. On the one hand, there's the oxidation of iron sulfide minerals, I should say, for example, pyrite, and the oxidation process results in the formation of sulfuric acid, and you get a reduction, a decrease in the pH of the water. On the other hand, any calcium and magnesium carbonate minerals that present can react in response to that acidity and neutralize the acid and cause the pH to increase. So just some general terms that we use in this area. Acid rock drainage is basically the acidic condition that results from an excess of acid-generating minerals in the mine waste. If excess acid-neutralizing minerals are present, you can prevent the development of acid rock drainage. Metal leaching basically refers to the release of metals by weathering processes, and metals can be released irrespective of whether acid conditions are developed, and that's an important aspect of this kind of work. Engineered technologies can be used to limit metal leaching and acid rock drainage, and these are the kinds of things that will get developed and explored as the mine plan develops. So the typical geochemical questions that we would ask are what is the degree of imbalance between the acid generating capacity of a material and the acid consuming capacity of a material? We also look at what the rates of important chemical reactions are and how soluble the trace elements are under prevailing pH conditions. So just to say a little bit about the geological context of Pebble, we heard a lot about this yesterday, so very briefly, Pebble is an example of a porphyry mineral deposit. It's in the calc-alkalic subclass of these kinds of deposits. It's geologically similar to a large number of porphyry deposits that have a mining history. So likewise, some of the geochemical data shows similarities with Canadian porphyry mines, and some of my colleagues in SRK have worked on some of these other Canadian porphyry mines. So this experience base provides a large analogue data set which can be used to support geochemical predictions of how wastes might behave at the Pebble, in the Pebble project. So this is an important part of the geochemical toolbox. This is a sort of schematic geological cross-section of the Pebble site. It's roughly running from west to east. Most of the section's occupied by the porphyry mineral deposit itself. You can see that there are two mineralizing intrusions, one in the west. I'm pointing at it as if you can see, but you can't. I'll just try and talk through it. At the very left-hand side of the diagram, you've got the western mineralizing intrusion, and then there's another intrusion in the east, and the central region of the deposit's occupied mainly by volcanosedimentary rocks. The whole porphyry mineral deposit, it dips to greater depth towards the east. And it's overlain in the east by younger rocks, younger tertiary deposit rocks. Thank you. Okay, well, the lines on the cross section there represent drill holes. And the sort of red colours and the pale blue colouring is actually intended to illustrate the copper and the gold mineralisation levels as a function of depth in those drill holes. And you can see that the intensity of the mineralisation is greatest towards the peripheries of the deposit. And as we heard yesterday, most of that mineralisation is sulfide-based, copper in chalcopyrite. There's also gold associated with pyrite mineralisation. The younger tertiary rocks don't host economic mineralisation, but sulfides have been recorded in those rocks. One question that was raised yesterday was, what is the distribution of pyrite in the geology at Pebble? And clearly that's a very important question. The types of waste materials that might be generated by a mine there, their acid rock potential is going to be very much dictated by the levels of pyrite in the different kinds of wastes. And as we heard yesterday, the Pebble geology team are still developing their kind of spatial model of exactly what controls the pyrite distribution in the system. But when we came to plan our sampling program for our geochemical characterization, we wanted to try and capture the range of pyrite contents in the different kinds of materials. And to do that, what we did was we had a look at some of the other data that's in the drill hole database. And as well as copper and gold contents, they collect data for other elements, and one of those elements is sulfur. And sulfur is one of the main components in pyrite. So basically the sulfur distribution in the drill hole database can be used as an indicator of the distribution of sulfide mineralization. So what we did was we took, basically all our samples were going to be sourced from the kinds of core material that was generated during the exploration program. And what we did was we looked at the data in the drill hole database and tried to see whether we could target certain categories of samples in terms of their sulfur content. So I'm going to show a couple of diagrams like this. These are actually frequency distribution diagrams. What's along the x-axis here is different categories of sulfur content. At the left-hand side of the diagram, there's very low sulfur content. And then as you move towards the right-hand side of the graph, you go towards higher sulfur contents. On the y-axis is basically the number of samples that fell into those particular categories of sulfur content. And this particular graph shows data from the Pebble East zone, from the mineralized pre-tertiary. And I mean, there's a lot of information here because we've actually differentiated the different lithological types so that there are separate coloured bars for each different lithology. But the general point, the general sort of take home from this particular graph is that some of these samples have very significant sulfur contents. I should say also that this particular set of data that's plotted here was data that was it was data that was from samples that was from that were taken from material that was below the then economic copper cutoff grade, the copper equivalent of 0.6, and that was the cutoff grade that applied in 2007 at the time that this sampling exercise was undertaken. I think the copper cutoff grade that's being used now is a little bit lower than that. It might be something more like 0.4. So clearly some of these analyses that we've done will have to be revisited and refined as the kind of mine planning develops. But just to summarise, in terms of the pre-tertiary mineralised rock, there are very significant sulphur contents, and there are some concentrations at particular. There's a sort of trimodal distribution. You've got a first concentration here at relatively low sulphur contents, and then a second one here at 2 to 3 weight %, and then a third one here at very high sulphur contents. And if we just compare that with the same kind of diagram, but this time for the overlying tertiary deposits, you can see here that the distribution of sulphur is really quite different. There's most of the samples fall in this very low sulphur content range of the data. But note here, there is a secondary peak here at significant sulphur content. So even in the overlying tertiary rock, there is some degree of sulphur mineralization. And what we will do as time goes on is try and get a picture for exactly what controls the distribution of that sulphur and whether it can be related to some spatial control within the deposit and identified in advance when they come to mining this particular material.
Excuse me, your horizontal axis with range, is that in percent or parts per million?
It's percent. This is basically a plan map just to give you a feel for the distribution of the boreholes that were sampled for the geochemical characterization program. You probably can't see it all that well. There is a yellow line that marks the extent of the general deposit. And you can see that the sampling program's taken place over a period of several years. The first main sampling program was in 2004, and that focused on the Pebble West zone. And so the green dots over in the west here focus on sample material from the Pebble West zone. And then in 2007, after the Pebble East zone deposit was discovered, we actually extended the geochemical program to include samples from the Pebble East zone. And those are marked by the red dots here. And there's been a number of other supplemental smaller sampling programs that have taken place over time. In general, though, we feel that we've got fairly good spatial distribution of the deposit. So just to go over some of the specific study design questions. Firstly, we did a range of static tests, and Kirk introduced what a static test actually was earlier. But we did a range of static tests to look at the potential for metal leaching and acid rock drainage from a range of different sample types. We basically collected samples from the pre-tertiary mineralized material. We collected samples that were both ore grade and sub-ore grade. We collected samples from the overlying tertiary material. We made sure that we captured a range of lithological types. I guess our primary sampling criteria related to the sulfur content, as indicated by the drill hole database, and we also used information on the calcium distribution in the database, using the calcium as a surrogate for the neutralizing potential of the materials. So our aim really was to capture data for as wide a range of different kinds of geochemical materials as we could. We've also studied tailings. Tailings have been supplied from concurrent metallurgical studies. To date, we've studied maybe 40 or 50 tailings samples compared to over 1,000 waste rock samples. Other study design questions related to site-specific waste management criteria. What we wanted to do was to identify those categories of materials that needed to be managed as potentially acid generating, as PAG materials, versus those materials that could be considered non-PAG or unlikely to generate acid conditions. We also wanted to collect data to give us some indications for how long it would be before the onset of acid conditions. I mean, even if a sample is actually categorized as PAG, as potentially acid forming, if it has any neutralizing capacity at all, it will take some time for that capacity to be consumed and depleted. So there may be some time period over which that material won't be acidic. And those kinds of questions are very important when it comes to making management decisions. We also wanted to collect data that could be used to support water quality predictions, but I will make the point that we can't really go too far down that road until we have a mine plan to put the whole process into context. Now, this slide gives a lot of information. You don't necessarily need to assimilate everything there. I really just included it to give you a feel for the numbers of samples that we've studied and the range of test techniques that we've used. As I mentioned earlier, most of the focus in terms of sample numbers has been on static test work, in particular acid-base accounting. And you can see that there's, we've studied around 600 samples from the west zone, over 400 samples from the east zone, and 48 samples of tailings. And I guess our main categorization has generally been whether the materials are pre-tertiary or from the mineralized material, or tertiary from the overlying tertiary deposit. But lying underneath those main subcategories, we've also considered other subcategories of material types. We've done a smaller number of tests for some of these other techniques like mineralogical characterization. Shake flask extraction tests are static tests where you contact the solid with water and measure the chemistry of the water after the contact. The tests listed towards the end there are all kinetic test techniques, and I'm going to say a little bit more about them in some of the slides that follow. So this slide just illustrates some of the results that we've taken from the acid-base accounting test work. What's shown here is the neutralizing potential here on the y-axis, plotted as a function of the acid potential on the x-axis. Now, if the material has an excess of acid generating capacity, the samples will plot in this region of the diagram here and would be classed as potentially acid generating. And you can see that a lot, or most of the samples that were sourced from the Cretaceous, the mineralized rock, plot in that PAG region of the diagram. Over here, towards the left-hand side of the diagram, you have an excess of neutralizing potential, and those materials would be classified as non-PAG. And most of the tertiary samples sit in that non-PAG region in the diagram. Now, I've shown some lines on the diagram. One of these lines here shows the position where the acid potential equals the neutralizing potential. Now, you might say that, okay, one side of that line, it's PAG, the other side of the line is non-PAG, but you also have to consider the rates at which the different components of the sample are reacting. If neutralizing potential were to be consumed faster than the acid potential, then you'd need more neutralizing potential in order for that material to be non-PAG. So, for instance, if neutralizing potential was consumed twice as fast as acid potential, you need 2 times as much neutralizing potential to be sure that that sample would stay neutral. So basically, there's a region of uncertainty where you don't really know for sure whether it's PAG or non-PAG, and one of the aims of kinetic test work programs is to try and identify the relative rates at which these different components of the samples react, so that you can define where that boundary should lie. So to move on to reaction rates, as I mentioned before, there are a number of methods available to us for measuring reaction rates. One of the most common is the humidity cell test. Humidity cell tests have relevance to exposed rock, so rock that might be stored in a waste rock facility, stockpiled, or exposed on a pit wall. Basically, the humidity cell test involves loading crushed sample material into a cell, and the photograph on the left shows humidity cells. And the sample is then rinsed weekly with deionized water, and the chemistry of that leachate water is monitored. In between rinse events, the sample's maintained in a moist aerobic condition, which is designed to maximize the conditions for sulfide oxidation. So basically, while the sample's sitting there exposed to air and to moisture, it's reacting and it's generating reaction products, which are then washed out of the sample during the rinse event. And you can measure the mass of solid, or the mass of solute, I should say, in the leachate, and that gives you a measure of how much mass of reaction product has been generated during that time. We've done quite a lot of tests using the humidity cell technique. We've done a smaller number of tests using other non-standard techniques, and one of these non-standard techniques was barrel tests. Now, these barrel tests are designed to evaluate weathering behavior under field conditions, and you can see there that's a photograph of barrel tests, and they're actually set up in the field in the sorts of conditions that you would expect a waste rock facility to experience. Basically, what we have is This photograph here shows is looking down into one of the barrels, and you can see there's rough crushed material here. It's a coarser particle size than the lab tests, but it's not as coarse as you would expect in a waste rock dump. The top of the barrel's open to the elements, basically, so every time it rains, rain will percolate through that material, and there are buckets here underneath the barrels that collect any water that passes through the solid. And water that collects in those buckets is collected periodically and analysed for all the same elements that we analyse in the lab program. Now, we also wanted to collect data that was relevant for reaction rates underwater, and I just want to talk a little bit about that to put it into the context of the kinds of mine features that we're targeting here. On the one hand, if waste rock material has been identified as PAG material, one of the engineering options available is to store that material underwater. So there's a need there to collect data that can describe reaction rates that apply for underwater conditions. The other kind of mine feature that we're targeting here are features like rock that's exposed, say, underground, if an underground mining method was adopted for any part of the deposit, or pit walls. Now, those particular mine features are going to be weathering and oxidizing for the period of time that the mine is operating. But on mine closure, some part of those features or all of those features might be submerged by water as groundwater table rises again following flooding. So we wanted to design some tests that could generate data that might be relevant for those kinds of scenarios. And the two tests that are particularly pertinent here are the bagged weathering tests, and I'm going to show a photo of those in a second, and also subaqueous column testing. So this slide shows some photographs of these different tests. Now, the bagged weathering test here it's really very simple. It's a big plastic bag with holes in, and crushed rock is placed into those bags, and it's just left on a pallet in the warehouse. And that crushed rock in the bag is basically being stored in moist aerobic conditions in a very similar way to the materials in a humidity cell test. But the main difference here is that the material's not being rinsed periodically, so any reaction products that are forming in those materials will continue to form and are not washed out of the sample. And what we do is we've had these tests. I mean, each test is about 15 kilograms of rock in a big plastic bag, basically. And periodically, we take a small subsample and we do a shake flask extraction test. And basically, the intent there is to monitor how much reaction product has accumulated in the sample during the time since that stored bag was initiated. After some period of time, I guess our hypothesis is that the reaction products that form might coat the surfaces of minerals and cause reaction rates to reduce. And so over time we expect that the rate of accumulation of reaction product will start to slow down. And this, in fact, is what some of the data does show. At the time that we deem that no further reaction products are forming, we can take those samples and submit them for subaqueous column testing. And this photograph here shows some subaqueous columns. Again, it's kind of a similar scenario to a humidity cell test. Basically, there's a crushed rock sample in a column. The main difference here, though, is that the sample's completely submerged in water. every week, the pore water is removed from the base of the sample. I don't know if it's very clear from the photograph, but above the sample there's a kind of a head of water here that's about twice the height of the sample. So when water's removed from the bottom of the sample, fresh deionized water is put into the top of the column to make sure that that head of water always remains in place. Because the sample's always completely submerged in water, the rates of solute release that you monitor in the leachate are pertinent to reaction rates under subaqueous conditions. So just a little bit of a summary of what the kinetic test program has involved for waste rock. We've used a range of methods. The focus has been on humidity cell testing, which is the more standard technique. And using that technique, we've done to date 66 humidity cell tests for waste rock. And we've supplemented the data from the humidity cell test program by data using a number of other non-standard techniques. Basically, for a smaller number of samples, the idea being to complement the kinds of data that we get from the humidity cell tests. The samples that we've selected for the kinetic test program have covered a range of material types. We've got both pre-tertiary and tertiary material types in these columns. We've got a range of lithologies, a range of sulfur contents, and sulfur being, if you like, an indicator of the pyrite content of the material. A range of neutralizing potentials and a range of metal contents. I would like to make the point that the rates that we measure in these tests apply to the very carefully prescribed conditions of the laboratory test. And before they were applied to a full-scale mine feature, there would be some element of scaling required. For instance, a waste rock dump will have a proportion of material that might be a similar grain size to the grain size of the material in the lab test, but there will be a proportion of the material that is much, much coarser. And reaction rates are very much a surface area controlled effect. So the higher the surface area, the smaller the grain size, the faster the reaction rate. So in scaling some of the laboratory-derived rates to a full-scale system, there needs to be some background of the change in the physical characteristics of the material you're trying to model. So I'll just go in now to some of the outcomes from the kinetic testing program. Here are some example results from humidity cell tests, and what's shown here is the pH in the column leachate as a function of time. And these data here are from 6 different columns, and they show different kinds of behavior. These 2 columns here have actually remained pH neutral for the duration of the test, and the test duration here is some 4 years actually. So these are long-running tests. These tests in the middle here were initially pH neutral, but over the duration of the test have tended towards more acidic pHs. And then there are a couple of samples here where the pH was immediately acidic. So we can use this kind of data to get insights to the time lag to development of acid conditions. What we've also tried to do is relate some of the outcomes from the test work to characteristics of the samples. And here this plot is a plot of the average sulfur release rate from the column, plotted as a function of the total sulfide content of the sample. What's shown here are data from pre-tertiary mineralized rocks. And I think you can see that there's a fairly clear positive correlation between the sulfide content and the sulfate release rate. And the relationship doesn't seem to be all that strongly influenced by the pH of the solution. I've indicated which solutions corresponded with acid leachates by putting dotted circles around the outside of the data point. So you can see there's a cluster here towards the higher sulfide content, which gave acidic leachates, but there's also quite a few down here with low sulfide contents, which also gave acidic leachates. But all of them fall along a very, very constant trend here. And basically we would hypothesize that we could use that relationship to extrapolate beyond our data set, if you like. If the mine plan, when it comes into being, shows that the total sulfide content of waste materials goes beyond the range that we've got measurements for here, perhaps, let's say for argument, up to 50% sulfur. Unlikely, I know, but we could argue that you could extrapolate according to the trend here, and you could calculate what the sulfate release rate for that sample might be. Now, I mentioned earlier that there was a degree of uncertainty as to how you differentiated PAG and non-PAG rock on the basis of static test results, because you need to consider the relative rates of consumption of the acid potential and the neutralizing potential. And what we've tried to do is use the kinetic test data to help us identify where that criterion should be. And how we've done that is we've looked at, on the one hand, the calcium and magnesium release from the leachate data. We're using the calcium and magnesium as an indicator of the reaction rate of calcium and magnesium carbonates. And what we've done is we've compared the release rate of calcium and magnesium to the release rate of sulfate. Sulfate being an indicator of the rate at which the acid potential is being depleted. And I think you can see that as you go towards, I should say that this ratio is plotted as a function of the sulfate release rate. So for higher sulfate release rates, the data points start to lie along a horizontal line here. Now, the grey shaded area here basically shows the bounding ratios that correspond to the theoretical relationship of carbonate-based neutralizing capacity. So basically, theoretically, you'd expect the ratio to be between 1 and 2. And a large number of the data points do plot inside that bound, but closer to the 2 than the 1. And basically, what we've said is that for the pebble rocks, we think that site-specific criteria should lie around 1.6 based on the information shown here. And we think that ratio is actually equivalent for the tertiary rock and the pre-tertiary rock. One of the other things that we want to try and get a handle on is the timing to the onset of acid conditions. And basically that time is a function of the amount of neutralizing potential that's present in that sample and the rate at which that neutralizing potential is being consumed. So you can calculate a time based on, the one hand, the neutralizing potential, and the other hand, the rate of consumption. And what we're doing here is we're relating the rate of consumption to some of those earlier characteristics that I showed. If you can cast your mind back to that graph that showed the sulfate release rate as a function of sulfide content, that basically, the sulfide content is an indicator of the acid potential, and the little k here is basically the gradient of that trend, that line on the graph. So if you know the acid potential and you know what the gradient is, that little term there is telling you how quickly the acid potential is being consumed. And if you know what the relative rate of consumption of the neutralizing potential is to the acid potential and multiply that into this term here, you get the rate at which the neutralizing potential is being consumed. So we actually did those kinds of calculations based on the humidity cell test results. And what we calculated was, for a material that had a very low NP to AP ratio, the times to onset were very fast indeed, less than 2 years. For material that had an NP-AP ratio of 0.1 to 0.3, which is pretty similar to the median levels for pre-tertiary waste materials, the times to onset were of the order of 3 to 10 years. And then for higher NP-AP ratios, you started to get into the decade range. Now, we compared those estimates with some estimates that were based on core aging characteristics. Now, the core program, the very early stuff was done in the 80s, and then there's been, over the years, more and more new core has been collected. And what we did was static test work on very old core and newer core, and we collected some statistical data on, for instance, the average neutralizing potential in old core versus new core. And we did it as a function of core age, basically, and we showed that the neutralizing potential in the older core was consistently less than the neutralizing potential in newer core, which we would hypothesize was due to consumption of that neutralizing potential due to sulfide oxidation within the core while it was stored in the core shed. And we kind of extrapolated based on some fairly crude statistics, and based on the core aging data, we basically estimated that the onset to acid conditions was going to be of the order of 20 to 40 years. So based on the core data, the rates are somewhat slower than are being indicated by the humidity cell test. But there's a number of reasons for that. First of all, the humidity cell tests involve crushed rock material, so there's a high reactive surface area, and the rates are going to be accelerated relative to an intact core. The other thing to remember is that in the lab, the tests are being conducted at pretty much at room temperature, whereas the core is being stored outside. Here, this is at Iliamna, so the ambient temperature there is a lot lower, and so these are very plausible reasons for why the reaction rates would be slower in core material than in the lab tests. As well as acid rock generation, clearly we need to look at metal leaching and those processes that control metal leaching. So this graph shows the release rates for copper plotted as a function of pH of the leachate, and you can see that there's a very strong trend there. The highest release rates are associated with acidic leachates. And there's a trend towards lower release rates for neutral pH. So basically, one of the main controls on metal release or on copper release, I should say, is the pH of the leachate, the pH of the sample. So the potential for copper release is very much linked to whether the material is classed as PAG or non-PAG. But that doesn't apply necessarily to all elements. There are a number of elements, and especially I'm talking here about arsenic and molybdenum and selenium. These kinds of elements form oxyanion species in solution in oxidizing conditions, and by that it's basically a complex with oxygen in water that is fairly mobile under a wide range of pH conditions. And for those particular elements, there was no real relationship between the release of that element and the pH of the leachate. And in fact, in the case of selenium, the most significant release rates were actually measured for tertiary materials, non-PAG materials. These are just some example results from field weathering tests. These are the barrel tests that I showed you some photographs of earlier. Now, these tests are located on site. So during the winter months, they're actually frozen. So any sampling of those tests takes place during the summer months. And so basically here we've got some clusters of data that correspond to summer month sampling events, and then there's a sort of gap in the data during the winter when the tests were inaccessible for sampling. I'll just point out that there's more data shown on this graph than was actually presented in the EBD document. The EBD only showed data up to the end of, I think, 2009, whereas data here is showing up to the end of last year. And in general, you can see that in the very first year that the tests were running, the solution concentrations of copper were significantly higher than is generally being measured in later years. And that probably represents some flushing of pre-existing soluble salts that were present in the sample. So this kind of behaviour is analogous to the sorts of behaviour you see in lab tests, but clearly interpreting the data from these barrel tests is going to be a lot more complex, because the conditions that the barrels are operating under is kind of at the whim, if you like, of rainfall events. So there might be long periods of time between rinse events, or short periods of time between rinse events, depending on the rainfall for that particular year. This is just some average solution concentrations that have been measured in the different barrel tests. The barrel tests, there are 4 involving pre-tertiary materials and 6 involving tertiary materials. Now, all the pre-tertiary materials are PAG. 2 of them are generating acidic leachates, but 2 at this point in time are still generating neutral leachate. The barrels that have gone acid are giving the highest dissolved copper concentrations. But have a look at the selenium data here, and you can see that the most significant dissolved selenium concentrations are actually in these 2 barrels here, which are the pre-tertiary granodiorite monazite, I think N is. So, you know, the behaviour of selenium is not so easily linked to the pH of the leachate water. So just some general observations based on the field test results to date. 2 of the barrels have acidic leachate. These involved pre-tertiary PAG-classed materials, and we've got very similar results in the lab testing programme. There are broadly similar trends in leachate chemistry for both the field and the lab tests. Arsenic, molybdenum and selenium associated with leaching of pre-tertiary and tertiary materials. Higher metal contents like copper is leaching from the pre-tertiary material. How much time have I used up already?
Another 5 minutes.
5 minutes, okay. These are some results from subaqueous columns, and again you can see that there are trends that can be related to the pH of the leachate. This picture here on the left is the pH in leachate as a function of time. Now, 2 of these samples had already gone acid before they were submitted for the subaqueous test, and they have consistently generated acidic leachate for the duration of those tests. Compare that with these samples up here, which have remained near neutral for the duration of the test. And if you look at the copper leaching behaviour, you can see that the highest copper leaching under these subaqueous conditions is also linked with the the acidic leachate test work. Arsenic behaviour is a little bit more complicated. One sample showed very high arsenic leaching in the first 2 years in pH neutral leachate, but in later stages of the test, the arsenic leaching has decreased. But if you look at this this sample here, which is one of the acid leach tests, the arsenic leaching in that particular test is increasing with time. So clearly there's a lot of interpretation we have to do to understand some of the trends in metal leaching that we're seeing in these tests. I'll go very quickly, I think, through the tailings data. We've done the same kinds of work for tailings that we've done for the waste rock, and this is a very similar plot. It shows the neutralizing potential plotted as a function of the acid potential. Now, to date, the type of tailings samples that we've studied have all been bulk tailings, low sulfide tailings. And so generally, the samples plot in the non-PAG region of the diagram. There are a few of the more recent samples that have strayed into the higher sulfide content range and plot as PAG. This graph shows some results from humidity cell testing for tailings, and on the y-axis we have the sulfate release rate as a measure of the rate at which the sulfides are oxidizing, and on the x-axis we have the total sulfide content of the sample. And there's a similar trend towards higher sulfate release rates for higher sulfide content samples, similar to the trend that we saw in the waste rock data. What's also shown here is that there's a grain size effect, that the tailings have ranged from very fine tailings slimes to coarser tailings, the sands. And I've tried to illustrate that by using different sized symbols on the graph. I don't know how clear it is to people looking at it, but basically the smaller the dot, the finer the grain size of the sample involved. So if you look just at the smaller dots, you can see that for a particular sulfur content, the rate at which that's reacting is faster than the equivalent sample for a coarser grain size. But if you look only at one particular category of particle size, there is a kind of upward trend as the sulfide content increases. So just to summarize the waste rock data, we've got a large database of static test data that have demonstrated some distinctive characteristics in terms of the geochemical behavior of different categories of waste materials. The kinetic test data sets suitable for input into waste rock management planning and water quality predictions. And we have some comparative data from field tests which allow the lab test data to be linked to field conditions. Tailings, we've got a fairly limited set of data for tailings based on one particular type of tailings, and that basically indicates that that particular type of tailings has a low potential for acid rock drainage. So I just wanted to say a little bit about the kind of work that's ongoing and planned for the future. Recently, the geological model for the Pebble site has been evolving towards differentiation of different alteration domains within the mineralized zone. And this basically took place around last year. And what we've done is we've reassessed the geochemical data set that we've collected in the light of those geometallurgical alteration domains. And as a consequence of that, we've identified some additional samples that we need to characterize to get good coverage of the different alteration types. We're also characterizing new tailings blends as and when they become available from the metallurgical testing program, and some of the recent tailings samples include peritic tails. And so we would expect those tailings to have very different characteristics to the tailings that we've studied to date. We also plan to do more detailed interpretation and modelling. What we need to do, we haven't done yet, is quantification of the field-based reaction rates from the barrel test work. I mean, as I mentioned, the interpretation of those those data sets is going to be a little bit more complex than the controlled laboratory conditions of a humidity cell test. But nevertheless, we need to try and calculate rates from those barrel tests so that they can be compared directly with equivalent data that's been generated in the lab. We're also going to do some geochemical modelling of the leachate chemistry data to try and identify mineral solubility controls that have applied in the tests, in the laboratory tests, and which we could assume could be relevant for the in situ field case. And we also will be developing conceptual models to conceptualize how the laboratory-derived data can be scaled up for application to in situ large-scale field conditions. And we'll do that as and when the mine designs become finalized. And that's everything I had to say. Waste rock. Actually, it might be easier. I think I meant to do this as I was going through but I didn't. If I go back to that geological cross-section. Okay, I mean, I mentioned there's no finalized mine plan, but clearly whatever mine plan is settled on and whatever mining method is used, mining will target the mineralized rock, obviously, because that's where the metal is, that's where the ore is. So material from this zone here, a proportion of that material will be considered economic and would report to a processing facility, and the metals would be removed and sold to market, and the waste product from the processing facility then becomes tailings, and the tailings are a particular waste form that would be managed in a particular way. But some proportion of that mineralized material will not be economic to process, and that material would report directly to a waste rock facility. So that material would be categorized as waste rock, as opposed to tailings, which is a waste product from the processing facility. And generally speaking, if we look at this cross-section, within the mineralized material, we don't know what tonnages are going to be classed as economic and would be processed versus, what tonnages would be classed as sub-economic and would report to a waste facility. But we do know that the overlying tertiary material doesn't host any economic mineralization, so the entire tonnage of that particular category of material that's mined would report to a waste rock facility. So in terms of qualitatively speaking, in terms of the waste rock tonnages, it's likely that the tonnages would be dominated by tertiary material rather than pre-tertiary material. Does that answer? Yeah.
Thanks. Thank you very much, Claire. That's a lot of information. It's so much information we thought we'd give you a break.